Hello, class, and welcome to trigonometry. I want to explain a little bit about where the word trigonometry comes from. So, trigonometry comes from Greek words trigonon, and that means triangle, and metron means to measure. So you can expect that you're going to be doing a lot of measurements of triangles, both the angles and the side lengths. And it turns out there's many applications for trigonometry in the real world. So we'll be discussing that. And I'm going to start here with this angles. How do we represent angles, and some terminology that we're going to get it to use here. So let me come up here. Okay, so let's look at these three situations. So this first situation, we typically will measure an angle from an initial side, and then the terminal side is going to share the vertex at this point here. And if we go counterclockwise, then we're going to produce a positive angle. Okay, so alpha is this little character here, and that's the name of the angle that's the shortest positive angle that will reach this terminal side. Now I can go roundabout, and if I go clockwise, I can get to that same terminal side. We're calling this beta. That little B looking thing is called beta. But that's going to produce a negative angle. So if I were to take the absolute value of this negative angle, it's much larger than this small positive angle that meets at the same terminal side. I could create a much larger positive angle that also lands on this terminal side by going counterclockwise through the initial side, full rotation, and then back up to this terminal side. Okay, so we can name this angle gamma, this little character here, to differentiate it from beta and alpha. Now, notice that these are all landing on the same terminal side. So we have a name for that. So whenever two angles have the same terminal side, we call those coterminal angles. Okay, so alpha, gamma, and beta are coterminal angles, but they're just expressed differently. Okay, let's move on to what we mean by standard position. Okay, so if in this case here, standard position, we're going to use the origin of a Cartesian coordinate plane to represent the vertex, and then the initial side is going to coincide with the positive x-axis. And then if we make a positive angle, we're going to go counterclockwise to some terminal side, and then that's going to make our angle. Notice that I've got this angle here is a negative angle. Okay, and this character is theta. So both of these angles have been named theta, even though they are different angles. This one's a negative angle. This one's a positive angle. And just to remind you here, I could create a coterminal angle. In B here, I could create a coterminal angle that's positive instead of negative. All I have to do is, first of all, pick my pen. And let's make a new angle. And we'll call that alpha. It's coterminal with this theta. Okay, that's our standard position. Now, we can reference the quadrants. If you remember from some point in algebra, they discussed the quadrants of the Cartesian coordinates, and this is quadrant 1, this is quadrant 2, quadrant 3, quadrant 4. They've used Greek numbering here. I'm using. Okay, and we can see that since the terminal angle sits in quadrant 2, this theta lies in quadrant 2. In this case, it doesn't matter how we get to the terminal side, it matters what quadrants it's in. So this is a negative angle theta that lies in quadrant 4. And then we've got this special situation here. If I do not land on within a quadrant with my terminal side, then I land on one of the axes. It makes a quadrantal angle. So there's two more we could make here. I could make a quadrantal angle that terminates here, the positive y-axis, or I could make a 180-degree angle that terminates here along the negative x-axis. Okay. Then the rest of the angles are going to be in one quadrant or another. All right, so let's talk about 360 degrees. That's a single rotation back to the initial side. So if I have an angle whose terminal side coincides with its initial side, then we've done a full rotation and created a 360-degree angle. Okay. If I just go 1/4 of the way through 360, well, 4 fits into 90, or 4 fits into 360 90 times. So that's 1/4 of a full rotation, or 90 degrees. And then we've said this here for a halfway around, 1/2, 2 fits into 360 180 times. So this flat angle that has the terminal side on the other side of the vertex, it's 180 degrees. So why do we like 360? Well, we like it already because 90 fits into it evenly and 180 fits into it evenly, but 360 is a very friendly number in the sense that it will accept a lot of divisors. So another one is if I take 1/3 of 360, or if I take, so if we divide 360 by 3, then better yet, let's count by 30s here. Okay, so I know that 1/3 of the way to 90 is 30. Another 30 is going to put me at 60, 2/3 of the way to 90, and then we know this is 90 degrees. Okay, and I can basically just keep counting by 30s because I know 30 evenly divides 360. So after the 90, we're going to get 120 degrees. If we reach this 150 degrees here, and then we add the 30 to that, and we should be at 180, which is where we are. And then another 30 here is going to be 210 degrees, 240, 270, 300, 330, and then 0 is the coterminal angle with 360. If we go all the way back around, we're at the same place that we started with the 0 degrees. Okay. Oh, well, while I'm at it, another friendly divisor of 360 is 45 degrees. So we can fill this out even more. So halfway to 90 is 45 degrees. 45 more is 90. We've already got it. But now we don't have this split in half here. So if I add another 45 degrees to the 90, then I'm going to get 135 degrees. Add another 45 degrees to that, and we hit the 180 again. Okay, and then okay, and then if we take another 45 after 180, we're going to hit at 225. Another 45 degrees takes us to the 270, and then we add the 45 to that, and we're going to hit 315 degrees. Okay, so look at all these values that we can create if we use 360 as our measure for a single rotation. Okay. So if we needed to draw each of these angles, now we don't have to think very hard about it, right? We know that 45 is going to be this one. Negative 90 is going to take me down here. Okay, here's 45. If I go not positive, not counterclockwise, but if I go clockwise for negative 90, that's going to put me down here. So this is negative 90 degrees, 225. So if you remember, as we were doing this, 225 landed on that. As we were splitting it up with the 45s, we landed over here on 245. I'm sorry, 225. And what else do we want? We want 405. Well, look at that. That exceeds 360, right? So we're going to have to come all the way through to 360 and then add, how much do we add 360 to get 405? Well, 45. So we can see that if I do the, oops, the revolution, then this is also 405 degrees. So 45 degrees and 405 degrees are coterminal angles. Okay. All right. So we can draw those without this little Cartesian helper. And so those angles should be reflected based on our analysis here with the Cartesian initial standard position. Okay. All right, now we're going to move on to degree measure. How do we discuss degree measure? Well, we can think of it a couple different ways. So I could want an angle that doesn't land on a perfect degree is going to have some decimal part. So for instance, I might have an application where I'm required 50.75 degrees. Okay, so that's degrees format in decimal form. All right, but what if we want to use minutes and seconds? They divide the degrees where a single degree is equal to 60 minutes. So this little tick means minutes. This double tick means seconds. So first they define 1 degree to be 60 minutes, so we can further divide degrees into minutes, and then they define 1 minute to be 60 seconds. So we can further divide it. And we might come up with a measurement that looks something like this. Let's say some application requires an angle that's 14 degrees, 2 minutes, 21 seconds. Okay, so this is another way to think. So what we're going to need to do is convert between the two. So I should figure out how can I change this into the degrees, minutes, seconds, and then how can I change this into its equivalent decimal form. So this is okay. So those are our two formats. Okay, so we're back, and here we're going to try and convert from one format to the other because we know the definition that they've given for these formats is that 1 revolution is 360 degrees, 1 degree is 60 minutes, 1 minute is 60 seconds. Okay, so let's take this idea and just going to put this down real quick. So for part A, we want to go from 50 degrees, 6 minutes, 21 seconds to decimal. Okay, so I've just copied that here. We're going from 50 degrees, 6 minutes, 2 seconds to decimal. And we know that 1 degree is equal to 60 minutes. So if I divide those both by 60, I've got that this is now 1 minute. So 1 minute is equal to 1/60th of a degree. Okay, so let's keep that in mind as we do this. This part's already in degrees. We don't have to do anything there. So we got 50 degrees plus 6 minutes. But if I want it in degrees, then I know that's 1/60th. So I'm going to take that 6 of these minutes equals 6 of 1/60th degree. So 6 times 1/60 degrees. All right, so let's pop that in a calculator. We're going to take 6 and multiply it by 1 divided by 60. Okay, so that's 0.1. We're also adding 21 minutes, or 21 seconds, sorry. Now, what is 1 second equal to? Well, it's another 1/60th of 1 minute, right? So we have to take the 60, we're taking 1/60th times 1/60th, or 1/3600 in terms of degrees. So we're going to take this 21 times 1/3600 to get degrees. All right, so just know that you're going to take and multiply your minutes by 1/60th to get degrees, and you're going to take and multiply your seconds by 1/3600th, because that's a single second. All right, so back to the calculator. If I take 21 times 1 divided by 3600. Okay, so we're going to add to that 0.0058. We'll stop at the 8 there. All right, so if I tack these all together, I get 50 plus 0.1 plus 0.0058. So converting to degrees in decimal form, we're going to get 0.1058 degrees. Okay. All right, our next goal for part B here is to take and convert 21.256 degrees and rewrite it in degrees, minutes, second notation, rounded to the nearest second. Okay, so we've got 21.256 degrees, and we can abbreviate that as degrees, minutes, second format to the nearest second. So in this case, we've got to multiply, and we're going to take 21 degrees plus 0.256 degrees. Now remember that 1 degree is worth 60 minutes. So to get the minutes, we're going to multiply that by 60. And so we don't have a full degree, but we've got a portion of a degree. So we're going to chop into a full degree of 60 minutes by this. So I'm just going to take 0.256 times 60. And we still have a decimal part. So we've got 21 degrees plus 15.36 minutes. Okay, now we don't have seconds yet, but remember we've already multiplied this by 60 once, so we have to multiply the 0.36 by 60, because that's the portion of the minutes that are seconds. So we'll rewrite this as 21 degrees plus 15 minutes plus 0.36 times 60, because there's 60 seconds in a minute, and this is the portion of the minutes, and that'll create the format we need for seconds. So we're going to take that 0.36 times 60. Yeah, 21.6. So it's 21 degrees plus 15 minutes plus 21.6 seconds, but they want us to round to the nearest second. So we're going to round that up to 22 seconds. The 0.6 is 5 or better. Okay, so there's our answer to the nearest second. Okay, and back on the slides, we can see that they complete this for us as well on the slides, and just reproducing what we just did here by hand. Okay, so now what we're going to do is introduce a measure called a radian, which is an alternative to degrees as a way to measure these angles. You're going to see that there's a very natural correspondence between degrees and radian measure. But the first thing we want to do is discuss what do we mean by radian measure. So I'm going to bring up this little app that's going to show us what we mean by radian measure. Okay, so what we have here is a circle that looks like it could be easily placed in a standard position Cartesian coordinate, where the middle of the circle is the origin of the Cartesian plane. And so what they're showing us here is that the radius length of this particular circle is 2.83. So to describe what a radian is, I'm gonna start this little animation. And a radian, a single radian, is that. So I've just created an angular measure of 1 radian. The radian is basically, if I were to take the radius of the circle and lay it on the circumference, the distance from the origin to the point on the circle is going to be wrapped around the circle and create a radian. So you can just think of a radian as if the radius was made out of like a string, and you pulled the radius string off and laid it on the outer circle, the distance that it covers, the arc that it makes, is called a radian, single radian. And you can see that no matter what the circle's radius is, like look at this circle here, that's this little piece of pie here, inside it says that's 1 radian. If our circle had been circumscribed around that distance, it's a much smaller circle than the one they're showing here. However, if I laid a radius from that circle onto its circumference, it's going to create the same angular distance as this larger circle. So no matter what the radius is for a circle, 1 radian creates the same size angle universally. All right, and that's what this slide is meant to show us here, is that I've got this one circle with a radius of this green r, and if I lay that distance that's onto the circumference, I get this initial side and this terminal side, and it coincides exactly with this very same angle if I were to use a radius of length 3 instead of 1. You're always going to produce the same angle. And so since that's a fact, we like to have a circle whose radius is 1, and we'll be using that a lot. So let's move on with this notion. All right, so what does the number pi mean? Well, pi can be calculated from any circle by taking the circumference of the circle and dividing by its diameter. So that's what we're showing here, is how you calculate pi. Now, I think we all agree that a diameter is 2 radius, so we're going to change the diameter into 2 times the radius. It's the same length, so we know that pi is also equal to the circumference divided by twice the radius. Let's solve this for c. So I'm going to multiply the top and the bottom of both sides I'm going to multiply the both sides by the denominator 2r, and then that's going to leave c by itself. And over here, that's going to change this to 2 pi times r. Okay, so we know that the circumference of any circle is 2 pi r. We also know that no matter what the radius is, that the angle that it forms is always going to be based on the radius, what is the radian measure. So if we were to allow r to be 1, then we know that 2 pi is going to represent a full revolution. So we've just guaranteed here that the angle described by 2 pi is the same as the one for 360 degrees. So the full revolution in radians is 2 pi.